Hello, today we're going to be solving this air conditioning cycle design question. So you're asked to design a residential air conditioning system that employs R22 as the refrigerant. Effective humidity control in the house dictates that the evaporator temperature must be no warmer than 12 degrees Celsius. The condenser is to be located in a courtyard where the air can be as hot as 39 degrees Celsius. Due to size constraints which compromises the condenser, there must be at least 7 degrees Celsius temperature difference between the refrigerant within the condenser and the outdoor air. So given these constraints, you're asked to specify refrigerant pressures for the evaporator and the condenser that will maximize the system's COP. Assume the compressor is isentropic and saturated liquid exits the condenser. So there are three parts to this question. Part A is simply to indicate the state points on a TS diagram. Part B is to specify the refrigerant pressures, and we're doing that specifically to maximize the system's COP, and then part C is calculate the COP. So part A and part B will be design questions, and then part C will look a lot like a conventional air conditioning analysis. Okay, so let's get into designing this system. So we know that since it's an air conditioning system, this evaporator is going to operate inside the house. This is because the goal of this evaporator is to pull heat from inside the house into the system and then dump it on the outside. So the outside we know can get as hot as 39 degrees Celsius, and we're operating our condenser with at least 7 degrees difference. So at the very least, we're going to have this running at 46 degrees Celsius. We're told on the inside to create effective humidity control, we want to run this no warmer than 12 degrees Celsius. So this has to be less than 12 degrees Celsius. So in order to design our most efficient system, what we're going to want to do is make it as similar to a Carnot system with maximum efficiency as possible. So I'm just going to draw a small Carnot system here so we can use it as a comparison or starting point. So the big difference between our actual cycle and our Carnot cycle is that our Carnot cycle is going to operate entirely within this vapor dome. So it's going to start in the mixed region at state 1, get compressed up into a saturated vapor, then it's going to condense through the condenser, that's where it gets its name from, all the way into a saturated liquid. So this is state 2, this is state 3. And then it's going to have isentropic expansion to state 4. Now, in our actual system, we have some constraints. The first is that the compressor does not like to operate within this mixed region. So what we're going to do is we're going to push it all the way out into the superheated region so that the compressor can operate within the superheated region. But we want to do it in such a way that still looks as close to this Carnot cycle as possible. So we're just going to stick state 1 right on the saturated vapor region. Then it's going to go through isentropic expansion. This was told to us in the question. Then it's going to condense all the way to saturated liquid. This was also told to us in the question, but we can also see this is quite close to the Carnot cycle, and so this should give us our maximum COP. And then we have an expansion valve, and so unlike a turbine, an expansion valve can't operate isentropically, and so we're going to have some entropy gain between state 3 and state 4. So that is going to be part A. So part B was asking us to select pressures that's going to maximize the COP. And so for a Carnot cycle, our maximum COP happens if between our cold source and our hot source like this. And so looking at this equation, we can see to make this as large as possible, what we're going to want to do is we're going to want to take our cold source, make it as hot as possible, take our hot source and make it as cold as possible. And this makes intuitive sense. Another way of saying this is that the bigger the difference between the hot and the cold source, the less efficiently our system is going to run. And so if you were to have an even hotter day than 39 degrees Celsius, it's of course going to be harder to pump heat from this cold inside into that outside. So this also makes intuitive sense. Now we're told that this evaporator, so this is this evaporator. So this temperature, and this is really the nice thing about air conditioning systems is that, or all of these cycles is that pressure and temperature are related. And so we can actually control this temperature by selecting this pressure. So this evaporator temperature, we know it has to be less than 12 degrees Celsius. So we're going to select a pressure such that this line is 12 degrees Celsius or less. On the other hand, we know that to maximize our efficiency, we want to make this T cold or this evaporator temperature as high as possible. So what we're going to do, we're going to select a pressure that is as high as possible as long as the temperature remains below 12 degrees Celsius. For the condenser, it's the opposite. So we know that our condenser pressure has to operate in such a way that our temperature is greater than 46 degrees Celsius, so we can't bring it anywhere below the line. However, we know that to have our system operating as efficiently as possible, we're going to want to bring it as far down to this line as possible. So we're going to try to run it as close to 46 degrees Celsius as possible. So this gives us a chance to start to write out part B. Now to do this, we're going to take a look at table A8, and we know that in this saturated region, pressure and temperature are directly connected. So by selecting a particular pressure, we can guarantee we're going to be at a particular temperature. So table A8 is the saturated table for R22, the fluid we're working with. And so this one's organized by temperature. And so if we take a look at our temperature of 12 degrees Celsius, we can see that our saturation pressure is equal to 7.23 bar. So we're looking for an integer, so we're going to either want to go up or go down. And we know that if we go up, we're going to exceed this 12 degrees Celsius. So we're going to round down. It'll make our system slightly less efficient, but it'll be within our constraints. So our pressure of our evaporator is going to be 7 bar. Now for a temperature of 46 degrees Celsius, our saturation pressure is equal to 17.725. This one you're actually going to have to interpolate. 46 isn't directly on the graph, but once you interpolate, you'll get this pressure. And so similarly, this time if we reduce our pressure, we'll also reduce our temperature, which means we won't be meeting our 46 degree constraint. And so we're going to want to increase our pressure. So this is going to be our condenser pressure is 18 bar. Okay, so now we'll move on to part C. So part C is going to be a little bit more of a normal analysis. So in this one, what we're trying to find is the actual COP of our system. So we've designed it to maximize this, and now we just need to calculate it. So the way we're going to do this, similar to in the past, we're going to go through each state point and we're going to find the enthalpy, and then we're going to come back and we'll find COP. This method just is a little bit easier because you're able to find all the enthalpies at once, and that way when you open your book up to the tables in the back, you're grabbing everything you need, and then you can come back and solve the question. If you choose to first write out your first laws and determine everything you need and then find all the enthalpies you need, that's also a great method. So we have 4 states, 1, 2, 3, and 4. And we know for each one we need 2 pieces of information. So the first one is fairly easy. We know our pressure, specified at 7 bar, and we know that we're talking about a saturated vapor. Our state 2, we know our pressure is going to be increased to 18 bar, and we know that it's isentropic expansion through the compressor, so that means that our S2 is going to be equal to our S1. So we will grab our S1 when we are looking for S1 state point. So for state 3, this one, the pressure is still at 18 bar. Remember, we're assuming no pressure drop across the heat exchangers, and it is going to be saturated liquid that we're told in the question. And then for state 4, we know we're going through that expansion valve, and we're going to be expanding to back down to 7 bar. And the second thing we know about this, once you do a couple of these questions, you'll know this immediately, but because this is the first example I'm showing, I'll show you a little proof about the second piece of information we know about that. So starting with state 1, we know that it's a saturated vapor. We'll take a look at table A8 and we'll find our H1 is equal to our Hg at our 7 bar, which is 253.64 kilojoules per kilogram. We're also going to get S over here because we'll need it for the next state, 0.9117. Okay, moving on to the next state, we now know two things about it, this 18 bar and our S2, which is equal to our S1. Okay, so for this one actually requires a double interpolation. We're in the superheated table, so we are talking about table A9, and we'll spare you the double interpolation, though it's good to just know that getting from this state point to the enthalpy we're to write down will take a little bit of work if you're doing it on your own. So this H2 is 276.99 kilojoules per kilogram. Okay, state 3, saturated liquid. So we're going to take a look back at table A8. So at this pressure, our H3 is going to be equal to our HF, which is equal to 103.51. Okay, and then we'll just quickly take a look at this expansion valve to see if we can figure out what's the extra piece of information we know about state 4. So we'll draw our expansion valve here. We know state 3 is going in and state 4 is exiting. So we'll draw our control volume and write our first law. So we know change in energy with respect to time is equal to Q dot minus W dot plus M dot, and then all the associated energies. So we have our enthalpy, which is similar to internal energy. We have our any change in kinetic energy and any change in potential energy. Okay, and we have to make some assumptions, and hopefully by now you're getting pretty used to this. We're talking about steady state. That's how we're going to be analyzing all of our cycles. And we know that we're not given any information about that, and so typically if we're not given any information, we're just going to have to assume it's negligible. Now, this is very good for the analysis of a question. If you were designing this in real life, you would have to think a little bit more about the implications of these assumptions. So the last thing is our heat loss and our power. So we know that there's no power generated through a valve. And for heat loss, there probably would be some, so I should say no power. And there probably would be some, however, we're going to assume it's negligible in this case. And it's probably realistic that the amount of heat loss is quite small compared to the amount of energy that's changed by releasing that much liquid. So it's not that this doesn't exist, it's that this number is small compared to the other numbers in this equation. So writing this out, we can get that H3 is equal to H4. And so this is going to be true across nozzles where all these assumptions are made. So this gives us our state 4, which is equal to our state 3. 103.51 kilojoules per kilogram. Okay, so now we have all our enthalpies. We can go ahead and solve this problem. So what we're looking for in this question is our coefficient of performance. For ACs, we often denote that as beta. And as usual, what we're looking for in here is what we are looking for, what we're trying to achieve, which is our Qn. This is representing the amount of heat we're pulling out of our space, divided by what we pay for. And that's the power we're going to be putting into the system. Okay, so to solve for Qn, we are talking about the evaporator. So this one is operating between states 4 and states 1. So this one takes Q into it. And so doing our first law around that, and again, I'm going to do a slightly lazier version of first law, so we're going to incorporate all of those cancellations we made before. So 0 is equal to Q in. We're going to add Q in because it's being added to the system. And we know that there's no power generated, so we'll add m dot and we'll do h4, so what's going in? Minus h1. So that means Q in is equal to m dot h1 minus h4. Our compressor power, draw a small schematic, so this one has state 1 going into it, and state 2 exiting. And this one we're also putting power in. So again, slightly lazy version of first law. This time we're adding work into it. So we're going to add the compressor power. So m dot, and this one's h1 minus h2, which simplifies down to m dot h2 minus h1. So now coming back up to our coefficient of performance equation, we can write this out. This is m dot h1 minus h4. This is m dot h2 minus h1. So the m dots cancel out. And since we've already looked up all these enthalpies, the hard part of this is really done. So 253.64 minus 103.51 divided by 276.99 minus 253.64. This gives us a coefficient of performance of 6.43. Just to put this final answer into some perspective, what this is saying is that for every 1 unit, or let's say kilowatt of power you put into the compressor, you're going to get 6.43 kilowatts of cooling power, which is kind of cool. Okay, that's it for this video. Hope it was helpful, and feel free to email me with any questions.